Good morning, everyone, and welcome to another live Quanser user webinar. So in this webinar series, we highlight the works of academics from around the world that use Quanser solutions and technologies. My name is Michel Levy, and together with my colleague Gemma Wang, we'll be your hosts and moderators this morning. Together, we're very excited to have our neighbor, Dr. Jinjun Shan from York University, to discuss how he has been using reinforcement learning and game theory techniques for autonomous vehicles and implementing these strategies on the Quanser self-driving car research studio platform. I'd like to welcome Dr. Shan again, and you can take the floor.
Okay, thank you, Mike, for your introduction. And first, I would like to share my screen. Okay, great. All right. Good morning, everyone. So my name is Jinjun Shan. I'm professor at Department of Earth and Space Science and Engineer at York University. So today, I will present our recent work on adaptive game theoretical decision making for autonomous driving vehicles. So the autonomous driving vehicles have many positive societal impacts, such as a safer and low-cost transportation system. It is estimated that the direct societal value will be between 0.2 and 1.9 trillion dollars annually by 2025. So 3 years from now. So by then, we will probably see approximately 8 billion autonomous or semi-autonomous vehicles on the road. So in the near to medium term, autonomous driving vehicles will operate in traffic scenarios together with the human driving vehicles. So where the interactions between autonomous driving vehicles and human driving vehicles will constantly occur. So that is this is the reason why we want to work on the autonomous driving vehicles. So here shows the 6-level driving automation defined by the Society of Automotive Engineers. So that's SAE. So now you can see there's 6 levels, level 0 to level 5. Basically, level 0 is fully manual. This is there's no automation at all. And level 5 basically is fully autonomous. So basically, each level represents a different level of intelligence. At present, most of the self-driving cars belong to level 1 and level 2. So again, so level 0 is no automation. Level 1 is the lowest level of automation. For example, the cruise control we use with our current cars, and this is level 1. And the level 2 basically is advanced driver assistance systems. And level 3 is the cars have environmental detection capability and can make informed decisions for themselves. So this is level 3. And level 4 basically is the cars can operate in self-driving mode. And level 5 basically is fully automation. So of course, and our goal is to reach level 5 automation. However, as I said before, so high-level automation needs high intelligence. So to achieve higher intelligence, self-driving cars need to be able to deal with several issues. So I just mentioned several. So for example, the road complexity, the traffic dynamics, and the behavioral randomness of the pedestrians. So those are just some issues we need to face in order to develop the fully autonomous vehicles. So actually, things I think in the last few years, and there have been significant advance in the self-driving car area. However, there are still some challenges. For example, the road testing of self-driving cars is costly and energy-consuming. It is estimated that the self-driving cars need to be running for about 300 million miles without fatality to assure the same rate of reliability as existing human driven vehicles. So, and also we need to consider the threat to the pedestrians when we do the road testing. And for self-driving system involves dynamic environment and complex interactions. Decision making is challenging since we cannot program rules to cover all traffic scenarios. So these are just some challenges we are facing, and we are trying to find some solution to these challenges. So in our research, we consider the decision-making problem for autonomous driving vehicles in urban traffic environment with unsignalized intersection, since there are more challenges for both human-driven and autonomous vehicles. And in our research, we choose to use a combination of deep reinforcement learning and game theory to model the different human driving behaviors in uncontrolled intersection scenarios. So we also developed so in order to do that, actually, we developed a realistic simulator using Gazebo and for the methodology, and we use game theory and deep reinforcement learning. So the question you may ask is, why do you combine the deep reinforcement learning and the game theory? So basically, reinforcement learning algorithm provide us with a learning mechanism similar to human learning. So where we eventually learn how to do things well through the trial and error. And the feedback from the environment can help us know if the way we are doing is correct. So this is the reinforcement learning. And the game theory basically is used to study the strategic reasoning and to model the behavior of interacting vehicles. So actually, one of the challenging problems using game theory is that the computational demand becomes increasingly heavy for a large number of interacting vehicles. But the machine learning techniques can move the computations offline and achieve decision rules for online use. So that is the reason why we combine the deep reinforcement learning and game theory for this problem. Okay, so here shows the end-to-end scheme for the self-driving car at uncontrolled intersection. So we have the low-cost sensor, which is a 2D LiDAR. So basically, the 2D LiDAR point cloud data and the car state are extracted through the long and short-term memory network, this LSTM, long and short-term memory network. So the 2D LiDAR point cloud data and the car state are extracted through this network to generate the observation information, so which is here. And the observation information is sent to the decision-making DQN algorithm. This is the DQN algorithm, deep reinforcement learning algorithm. And so then to get the speed command. Okay, so that is through the decision-making, we get the speed command for the self-driving car. Of course, that is only speed control, speed command. In order to control the self-driving car, we also need to have the steering command. And here we use the pure pursuit controller to get the steering command. So actually, I think I have one slide to show how to get the steering command later on. So in this work, and we propose an improved algorithm by combining the advantages of the traditional DQN, the double DQN, and dual DQ, and prioritize experience replay algorithm. So actually, this is a modified or this is an advanced DQ algorithm we use in our research to get the speed control. So here, basically is the D3QN pre-ER algorithm. Again, so we combine the traditional DQN, the deep Q network, and double DQN, dual DQ, and prioritize the experience replay as a PR. So we got the D3QN PR as our DQ algorithm to get the speed command. So I'm not going to talk the details of each one, and but if you have any question about that, we can discuss this later on. So basically, so once we have the DQN algorithm, next one basically is we can combine the game theory and reinforcement learning. So basically, that is so basically we want to generate the agent with different levels of reasoning for decision making. So that is to combine the deep reinforcement learning, the D3QNPR, the algorithm, with the level K game theory. So we are going to generate the different levels of reasoning. So then the basically, the level of reasoning for decision making in traffic scenarios, the learning capacity is offered by the D3QNPR, and then that is combined with the level K reasoning approach. So in the proposed approach and the predetermined non-strategic level 0 policy is anchoring policy from which all the higher levels are derived using the D3QN PR. But keep in mind, we have the level 0, and from level 0, and we have the learning algorithm, this is the D3QN PR, to get the level 1, level 2, and even higher level policy. For example, in order to get the level 1 policy, actually, if you look at the figure here, and we have the level 0, and from here we apply the D3QN PR algorithm, and then we can get the level 1. So basically, in order to get the level 1 policy, traffic scenario is created where all drivers are level 0 agents, except for the ego vehicle. Basically, the ego vehicle is the training vehicle we want to train to get the different policy. Then we will get the level 1 policy. And then if we want to get the level 2 policy, then we will have the scenario, and we assume all the vehicles have level 1 policy except for the ego vehicle, and then we can train and to get a level 2 policy. So basically, this is just the idea to how to combine the deep reinforcement learning and the game theory, level K theory. So on this slide, you can see two tables, and the first table is the training shows the procedure of obtaining the level K policy using the proposed approach. So actually, I already mentioned. So in order to get a level K policy, and we have the scenario, and then we assume all the vehicles have level K minus 1 policy. Then we train to get the level K. Basically, that is the table 1 says. And the table 2 basically shows the training process of adaptive policy in a similar way. So because the topic of this research is adaptive game theoretical decision making for the self-driving car. So then by the end of the research, we developed the adaptive policy. Okay, so I will show you later on. So as I said, so in order to control a self-driving car, and we need both the steering command and also the speed command. And the DQN algorithm is used to get the speed command, and to get the steering command, we need the pure pursuit controller. So actually, this figure shows how to get the pure how to get the steering command by using the pure pursuit controller, which is very simple. So here is here are the equations we need to get the steering command. So basically, the core idea here is we have the reference point, and this can be placed on the path, and basically this at a fixed distance ahead of the vehicle. So you can see this vehicle, and we have the reference point, and the steering command needed to intersect with the point using a constant steering angle, and this angle can be calculated, which is alpha here. So again, so this equation 2 to 5 are used to calculate the steering command for the self-driving car. So next one, so actually this slide shows the simulation and the experiment platforms we use in our research. So on the left, so basically this is the simulator we developed using Gazebo, and we can use this one to do many different simulations. And on the right, basically this is our experimental system, and we got from Quanser. That is a Quanser self-driving car research studio, which consists of 6 Q cars. However, in our research, we use only 4 cars. And each Q car is powered with the Jetson TX2 onboard computer and also a wide range of sensors. So actually, this figure is taken in my lab at York University, and we created this scenario for our research. So okay, so in order to do the simulation and hardware test, so here this table shows the action space and the reward function. So basically, the action space includes 5 possible actions that each vehicle can undertake. Basically, this is speed, okay? And maintain the speed, and accelerate, and fast accelerate, and brake, and hard brake. So these are the action speed of the vehicle has. And for the reward function, which is also shown on its table, so the reward function is used to evaluate the performance of the eco vehicle, which encourages eco vehicles to learn efficient human-driven behavior. So our reward function was designed to penalize the collisions of being in dangerous states and the reward efficient behavior such as reaching the destination or progressing. So actually you can see when you look at the reward function, you see we have the positive, we have negative. Okay, so this table shows the action space and the reward function in our simulation and hardware test. So yeah, so basically with the simulation and the hardware platform, we have done a lot of simulation and testing. So because in this work, and we proposed the D3QN PR. This is a new DQ method in our research and combined with game theory. And actually, we compare our method to different methods to show the learning efficiency. So actually, you can see we have this is our method, and we also have the double DQN PER and the dual DQN PER and D3QN and the double DQN and dual DQN. And here, this the last one, the brown one is the traditional DQN. So actually, to compare the learning efficiency and all algorithms were trained 8,000 episodes in an environment where all autonomous vehicles were level 0 reasoning. Okay, all are level 0 reasoning. And here you can see we got the result. So keep in mind that all the curves in the figure are smooth with a moving average over 300 episodes to get the smooth result. So from the result, we can see the prioritized replay and the dueling structure are the two most crucial components of the D3QN PR algorithm. If you compare those results, because they will remove, actually, if you remove either component, which and we will have the large drop in the learning performance. So actually, again, so the PER and the dueling structure are two most crucial components. And the nature DQN, which is the last one, and the dueling DQN, this is actually last two, perform worse during the training, which could be caused by the overestimation problem the DQN has. So basically, this is a comparison of different algorithms, and from here you can see the blue one, which is the method we used in our method, performs the best. And the next one basically just show you some training results. So according to the scheme mentioned before, we have successfully trained the level 1, level 2, and adaptive driving strategy respectively. So here I just show you some results. So after obtaining the training policy, and we first tested the two scenarios of eco vehicles being of level K and opponent vehicles being level K minus 1. Each for 1,000 episodes. Actually, this is the first two cases. Level 1, this is the eco vehicle, and level 0, this is the policy for all the opponent vehicles. And similarly, level 2 eco vehicle and level 2 is for the opponent vehicles. And actually, you can see they all have a very good success rate, which is 96.2% for the first one and 99.6% for the second one. So which means which meets the expectations of level K theory. And then the trained level 1 policy and the level 2 policy were tested on level K versus level K scenario for against 1,000 episodes. So actually, this is the case number 3 and number 4. So actually, all the vehicles have level 1 policy, and all the vehicles have level 2 policy. So now you can see this scenario has these scenarios have a much lower success rate because level 1 policy. Why? That is because if you remember, level 1 basically is conservative driver, and level 2 is the aggressive driver. So here, level 1 was level 1, we got 94.9, and level 2 was level 2, and we have 85.9. So the reason for the low success rate is because if considering the level 1, so actually there is the deadlock due to the conservative driving behavior, and for level 2, however, the low success rate is because the aggressive driving behavior will cause more collisions. Okay, so that is case 3 and case 4. So finally, we tested the adaptive policy because that is the contribution of our work, and one contribution of our work. And we tested the adaptive policy in 81 scenarios and also 3 other environments. So which consists of one type of level K model, and actually I think that is something like oh yeah, I think that is here. So then level 1 versus mixed and level 2 versus mixed, and also the adaptive this adaptive versus mixed. So basically, again, so we tested level 1, level 2 as the adaptive policy 1,000 times in the 81 scenario. So as you can see from the table, the adaptive policy has actually I think it should be okay. So now you can see for the adaptive policy, we have 96.2% success rate, which is also good. So actually, I also want to mention in this table, we also compare our method to the method used in our paper, in one paper, which is shown here. Okay, so because we just want to compare the performance of our algorithm with the autonomous vehicle controller developed in that paper. So basically, so we name our algorithm DRL. This is because it's based on the game theory and deep reinforcement learning, and the other one basically is the autonomous vehicle controller. So actually, you compare from the comparison, you can see this 96.2 and this 99, and we compare those. So the comparison shows that our end-to-end scheme integrating the perception, decision, and control has better performance in terms of the success rate than the results shown in this paper. So actually, you can see here, if you compare our method to that this method, and our success rates are higher than the other one. Yeah, so this makes sense because that is because the other paper, the method in other paper focuses on a simpler two-car interaction without considering the noise existing observation information. So they only consider two-car intersection, and we have more fancy or more advanced strategy. So that is comparison, and also we here is just a table to compare the policies in the mixed environment, as we said for the adaptive scenario, and we consider 3 different environments. So this also explains why for this one, and why we have different success rates. That is because if we have level 1 versus mixed, and then the deadlock is 4.3, and this is the dominant, and the collision is only 1.9 or 1.7%. However, if we have level 2 versus mixed, and then the collision is more because level 2 is more aggressive, right? So that's why the success is low. And if we have the adaptive versus mixed, and then the collision has been reduced quite a lot, and so that's why we have the success rate, which is 96.2%. So finally, I just show you some hardware test result, and this one basically is if you look here, this is case 1. This is L1, L2, L2, L2. That means the Eagle vehicle has, I believe, L1 as the level 1 reasoning, and the other vehicles have level 2 reasoning. And also the scenario is the Eagle vehicle will go straight. So basically, you can see the figure shows from a different time. The photo from at different times, 0 to 8 seconds. And here you can see this is the final result we got. So basically, so again, so from the result, it can be observed that when the level 1 and the level 2 vehicles interact with each other, the collision between them can be resolved. This is expected since level 1 vehicles representing the cautious drivers will yard the right of way, and the level 2 vehicles representing the aggressive vehicles will proceed ahead. So this is why the collision can be resolved. And the next one basically is L1, L2, L2, L1. So, and in that case, the eco vehicle will also go straight. So similarly, this figure shows the car 1 and car 4 controlled by level 1 policy interact with the car 2 and car 3 controlled by level 2 policy. The car 2 and car 3 enter the collision area first, and the car 1 and car 4 take the deceleration action to wait them to pass at around 3 seconds. So that makes sense because you can car 1 and car 4. These are the cautious vehicles because they have level 1 policy, and the level car 2 and car 3 they are more aggressive. So this why car 1 and car 4 will wait. Here you can see car 1 and car 4 will wait and the car 2, car 3 to pass the intersection first. Okay, so that is the case 2. And the case 3, I think that is similar. So this is a car 1 level 1 opposite. Car 2 is level 2, and all the other cars are level 1. So that means actually from the policy you can see car 2 will pass first, right? So actually you can see the result shown here. Now we can see the car 2 will pass the intersection first. And another one basically is L2 and L1, and L1. And then in this case, the eco vehicle will turn right. So eco vehicle basically is car 1 here. Okay, it is turning right. Okay, and here this shows actually the policy does work. And the next one, oh, actually, this is all the this is I think I show you 4. Sorry, 1, 2, 3, 4. Yeah, okay. There are 4 scenarios. I just 4 simulations. Sorry, 4 result. I just want to show you and to see to show you actually the policy we develop does work in different situations. And finally, I want to show you a video. Maybe I will start from the beginning. So basically, this is a video as a summary of our research, and our research is done by my PhD student Mingfeng Yuan, and also Kevin is an undergrad student working in my group last summer. So actually, this paper, this work has been published in recently on the IEEE Robotics and Automation letter. So here is the video just to show you what we have done. And here is the racial background, and you can see this is the intersection we want to we focus on, and this unsignalized intersection, and that basically that is the simulation environment. And again, so we developed the gazebo simulator so that we can run simulation. And here is the hardware test. And here you can see this is our lab, and we have 4 cue cards. We can do the we can run the hardware test in our lab, and also you can see all the cards, the states can be shown on screen. And I believe that this is level 1, level 2. Actually, you can see the policy of each vehicle. And actually, first we do the simulation, and then we do the hardware test. Here is the hardware test. Now you can see this eco vehicle is level 1, and this also level 1, and this is level 2 and level 2. Basically, that is I believe that is the case 2 we started, and the car 1 and car 4 are level 1, and the car 2 and car 3 are level 2. And here is offset. So car 1 and car 4 are level 2, and car 2 and 3 are level 1. So now this eagle is level 2, so that's why the eagle vehicle will pass the intersection first. So this one is eagle vehicle will turn in left. So again, so that is the simulation. Because it is level 1 and it is turning left, so it will wait other vehicles to pass. So in this case, and only car 2 is level 2. an illegal vehicle, and the other cars are all level 1. So that is a hardware test. So now you can see for all the cases, and the collision can be avoided. All right, so I think that is so that is the video I want to show you. And so conclusion. So basically, in this research, and we focused on the development of adaptive game theoretic decision-making strategy, and we combine the game theory and the deep reinforcement learning for the autonomous driving vehicles, and the interactions between the vehicles are modeled using the level K game theory framework, and it was shown that the adaptive model had a reasonably high rate of success in resolving the traffic conflicts and matching the expected behavior of each reasoning level, and we also developed the gazebo based simulator, so which allows us for realistic multi-vehicle simulation with various sensors and training strategies. And finally, the framework proposed in this work for modeling the multi-vehicle intersections can be used as a simulation tools for the calibration, validation, and verification of autonomous driving systems. So I think that is the end of my presentation. So I would be happy to take your questions.
Thank you, Dr. Shan.
Yeah, no problem.
That was a great presentation. Really appreciate it. So we have a few questions that have come in, and please feel to send some more.
Yeah.
Were your algorithms written in MATLAB, I believe, is the first question we got.
Yes.
They were,
you
right?
mean you mean whether the algorithm is written in MATLAB?
Yes.
I don't think so, actually. Sorry, I should I think my answer is wrong. No, I think we use the Python.
Okay. And for simulation, what software did you use?
For simulation, as I mentioned, we use Gazebo. So basically, we use a Gazebo to develop the simulator, and then all the simulation is done in the simulator we developed.
Okay, great. Thank you. Another question that came up was, so basically you're doing all your simulations and in an urban traffic environment, but the intersections don't have any traffic lights or anything, right? They're unsignalized intersections.
Yeah.
So why did you choose that particular scenario?
No, I think that is a very good question, and probably it seems to be weird to many of us, and why you have the intersection without the signal, right? But actually, I mean, because we are thinking of having the autonomous driving vehicles for everywhere, right? And not only for Canada, for our city. So the reason why we choose the urban traffic environment with the intersection and with unsignalized intersection, that is because that is a very challenging problem we have to face for the self-driving car. Actually, not only for the self-driving, but also for the human driving vehicles. Actually, I think when we decided to work on the scenarios, and we had some research, and we found this scenario is very challenging because it's also something we need to solve. Actually, just give you some numbers. Actually, according to the U.S., almost 40% of the traffic accidents in the U.S. are intersection related. And also, according to the U.S. Federal Highway Administration's report, almost 70% of the fatalities due to intersection-related traffic accidents happen at unsignalized intersections. That is the reason why we choose this scenario, and not because it's easy, because it's hard.
Okay, thank you. You definitely did your research. We have another question. Mr. Meskin wants to confirm that he just wants to double check that for controlling the Q cars, was Python used?
Yeah, we use the Python.
Okay. We have another question here. How does your method differ from self-play in reinforcement learning, and what are the advantages and differences with respect to that?
Sorry, can you repeat your question?
Yeah, so how does your method differ from self-play in reinforcement learning?
Uh, actually, you can see from my presentation, and we did combine different we can say supplements of the deep reinforcement learning, right? Because we combine the traditional DQN with the double DQN and duty DQN, and prioritize the replay buffer and the PR into the D3QN PR. And the reason doing that is we want to take advantage of each one and trying to increase the training efficiency. And actually, I think in my slide, and there's a comparison between the different training strategy, and you can see. I think I mentioned that. Just let me double check. So yeah, so actually, when we do the so when we compare different algorithms, and we found actually the during DQN and I think the during DQN and also the prioritized play critical role in the performance improvement. So and I can go a little bit further to say what is the difference between each supplement, because basically the double DQN handles the problem of the overestimation of the Q values. So that is the main purpose to use a double DQN. And for the during DQN, actually, we just separated the estimator of this elements. Basically, use two new streams. One is the one that estimates the state value. So this is V, and one that estimates the advantage for each action. This A. So basically, that is the purpose of, and this is the reason why we use the during DQM. And the idea of the prioritized experience replace the PR is that some experience may be more important than others for our training, but might occur less frequently. So we want to consider priority experience where there is a big difference between our prediction and the target, since it means that we have a lot to learn about that. So actually, basically, just give you some ideas, and actually, we did combine different aspects of the DQN to get the D3QN PR algorithm, and which perform the best in our configuration.
Okay, great, thanks. So just go through two more questions. Is there communication between the automated vehicles?
Actually, there's no for now. There's no communication between the vehicles. I mean, because we have 4 vehicles, because we do have central computer to do the training and to do the decision making. So everything will be sent to the central computer and to do the computation, and then will be deployed to each vehicle. So yes, the answer is there's no communication between vehicles. We can with the hardware platform, but we in our current research we don't have the communication between the vehicles.
Great, thank you. The last one is, you mentioned that your group developed your own simulator in Gazebo, right? Now,
Yeah.
Will that be publicly accessible? And yeah.
I okay. I had to ask my student whether we can make it public. and if they're okay, and definitely we can make the public. Actually, again, so the reason why we developed the simulator in Gazebo was because we need to do a lot of training, right? And we do have very good platform, the hardware system from Quanser. However, we won't be able to run everything, all the training using the hardware. So that's why we start to develop. I mean, my students started to develop the simulator so that we can do the training 24 hours and 7 days. And yes, and I think it works very well. And again, so I'm going to ask my students to see whether we can make it public. And if someone is interested in using that, please contact me.
Great, thank you so much, and thanks everyone. If you do have any more questions, after the webinar or whatever, please feel free to send it to us. And I encourage you to visit our website, and to view other how basically how users all over the world utilize our solutions as research validation platforms, as well as if you want to know about any upcoming webinars that are coming. We do a user webinar usually every month, so you can look forward to that. And on that note, yeah, I'd like to thank you again, Dr. Shan, and everybody. You can please have a great day, and thanks for attending.